Okay, so let's talk about adding a halogen to an alkene. If you're in my class and you're watching this, I suggest watching the video about adding an OH to an alkene before watching this, because some of the ideas are going to build on what we talked about there. If you're not, then you can ignore that and just watch this video. But my thought is we're going to talk about these four and their mechanisms. It's halohydrogenation, which we talked about this a little bit in recitation, radical addition of HBr, HCl, or something like that, halogenation, and Halohydrin Formation. So let's talk about those. So this is the chart that we had last time. We're still talking about Regio selectivity and stereo selectivity. That is, Regio selectivity is where on the molecule is it adding, more substituted, Markovnikov, or to the less substituted side, anti-Markovnikov. Stereo selectivity, syn being the same side, anti being opposite side, racemic being kind of all over the place. Also, I have in pink the colors for the things that we're adding the OH with, and in purple what we're adding halogens. So let's explain these. Halogenation here, this is halogenation as in like halogenation of alkenes. That's different from radical halogenation of alkanes that we talked about way back in the beginning of the semester. Totally different mechanism, although we are adding a halogen there. We have Halohydrin Formation. Also, sorry, back up. Notice how it's kind of straddling in between the anti-Markovnikov and Markovnikov. That's because I'm adding a Br to two different carbons. So it's neither really Markovnikov nor anti-Markovnikov because I'm adding the same thing to two different locations. So maybe you could say one is Markovnikov and the other is anti-Markovnikov, but that doesn't really make sense, right? Because it's the same atom that you're, or same element that you're adding to that carbon, whichever one. Now I have Halohydrin formation here. I have the halo a little bit more in the anti-Markovnikov, and I have the hydrin more in the Markovnikov addition. And we'll see why later. Also, both of these are anti. We'll explain that in the mechanism. Now we have Halohydrogenation. This one is extraordinarily similar in mechanism to the acid catalyzed hydration. The only difference is the nucleophile we're adding to the carbocation is a halogen, not water. Weird one, radical addition of HBr, or whatever. That one is weird. We'll explain that one in the mechanism. Both of these are adding racemic. Radical addition adding anti-Markovnikov, because radicals love to do anti-Markovnikov, and we'll explain why. It's very cool in the mechanism. Okay, let's check it out. So first off, halohydrogenation. That one is very simple. All we do for that one is we're just adding we'll just say Br. We'll use Br for all of these. I want you to pause it. Give this a try, because we talked about this mechanism last week. Give it a try to do this mechanism on your own. Check out my mechanism to make sure you get it. Okay. Here's the mechanism. Double check yourself. Notice how I added the bromine to the more substituted side. Originally, I ended up doing a carbocation rearrangement in the end. And I've added my bromine to the more substituted side. And it's racemic. Carbocation intermediates like to do that racemic thing. All right, there we go. That's that. Now let's talk about the weird one first, and then we'll talk about these two because there's similarities in their mechanism. So we'll just talk about the weird one first. Radical addition of HBr. We start off, we have HBr, and then we have a peroxide. So anytime you see a peroxide, you're probably going to be thinking radicals. And that's because these guys, this OO bond there is not stable. So let's look at that. First thing I think about here is I think about this OO bond being super unstable. So I'm just going to start off by showing the radical being generated. I'm going to do the single hook arrows like I always do with my radicals. I'm going to break this guy up. I'm going to end up with two things that look like this. They kind of look like magic wands, if you think about it. Anyway, I have HBr. I don't need to show both of them reacting. I'm just going to show one representative thing. So this HBr bond splits in half. It's called homolytic cleavage. It's where we evenly break the bond. One electron goes to each thing. So I'm going to end up making this alcohol, which is neutral, no radicals, and then I'm going to make the bromine radical. So that's really important because we need to generate this radical to be able to do our mechanism. So now this guy is going to react with our molecule of interest. So I'm going to split this in half. Now what that means is I need to give one of the electrons to either this carbon or this carbon. But I want to make sure that I have the more stable radical. So I'm going to give half of this bond, this pi bond, to this carbon, making it the more substituted. And I'm going to give the other half to connect with this Br here. Looks a little wonky, but that's okay. What I'm going to end up making is I'm going to make the more stable radical intermediate, which has the radical on that tertiary carbon right there. There's no way I can do resonance or something like that to stabilize that radical any further. So that's just where it's going to be. Also, this bromine is adding racemic. I could either add from the top face or the bottom face with equal likelihood, so I just put that there to show that it could be racemic. Now what am I supposed to do with this? Well, I have plenty more HBr to go along. So what happens is I take this radical, I attack, kind of combine with breaking this bond again, and I can regenerate my radical. So I've left that stereocenter on this carbon over there untouched, and now I create two racemic carbons on that spot. And I generate another bromine radical that can go on and do this reaction further. Okay. So let's write down what that would end up making here. So I've added the bromine to the less substituted side of where that alkene was. That is anti-Markovnikov, but racemic addition. Now let's talk about halogenation. Remember, this is different from radical halogenation. Another confusing thing, I'm adding the same exact reaction conditions, Br2 with CCl4. The only difference, I'm not having heat or light in this reaction, and I have an alkene. So it's not radical halogenation, because it's alkene halogenation. So let's look at that mechanism real quick. So I have Br2 with CCl4. The first thing I need to do is I need to remember that this acts as a nucleophile. And so I'm going to do this weird like push-pull type mechanism where my alkene double bond comes around, attacks this bromine, and kicks off this bromine. But all the while, so remember I've got lone pairs on this bromine, one of these lone pairs comes back around and connects there. So this is important because remember, alkenes, they're flat. They can be attacked by the top or the bottom face. And so I'm going to make this weird thing. It's called a brominium ion. I used to call it a bropoxide when I was a student. I don't know if my teachers thought I was annoying or funny, but I thought I was funny. But you make this brominium ion. See, it looks kind of like a bropoxide. You would think that they would be creative enough to like call it something fun, but it's fine. Brominium ion. And so I'm going to end up having two different possibilities. I could have that one, and I also will have one where my brominium ion is on the wedge rather than the dash. So I'm going to end up with both. And that's very important. So I'm going to end up with both of those. The next step of this reaction is I have Br minus, right? Because I kicked off that Br minus in this first step. The brominium ion looks a lot like a protonated epoxide, and we've talked about with protonated epoxides before how we are going to attack that epoxide looking thing from the more substituted location. So for a brominium ion, the nucleophile that's going to attack the brominium ion is going to attack from the more substituted side because it'll go through that carbocation-like intermediate. And if it goes through the carbocation-like intermediate, I want it to be on a more substituted carbon for stability. So this bromine, Br minus, is going to come in and do an like SN2 like reaction where it attacks, does like a backside attack and breaks that CBr bond there. As you could expect, I'm going to end up with something that looks like this, where I have my methyl now on the wedge, my new Br is on the dash, and this guy is broken and made a neutral Br. So you can see it kind of makes sense why I didn't really put that in the Markovnikov nor the anti-Markovnikov category, because I'm adding a Br to both carbons, so I can't really label it as either of those. That same kind of deal is going to happen over here. I'm going to have a Br minus come in and attack the more substituted side. So it's very important that you remember both of them. Oops. Also, it's very important that we show that these are adding anti. See, one's on the wedge and one's on the dash. It's very important that we remember to show both of them. And both of them showing as anti-addition. So let me draw those in. So I'm going to have two products. That phenyl stereochemistry has not changed. Cool. Now, Halohydrin formation is very similar. The reaction conditions are almost identical. I have Br2. Instead of CCl4 as a non-reactive solvent, I'm going to have water, which is a reactive solvent. So let's look at that mechanism. and see how that works out. Same start of the mechanism. I attack, kick off the bromine. One of those lone pairs comes back around. I'm going to make the brominium ion once again. And I'm going to make both the wedged and the dashed versions of the brominium ion. Now, remember when we talked about the thing like 5 seconds ago about how you have to add the nucleophile to the more substituted side, and how last time it kind of didn't really look like it mattered too much because the only thing I'm adding is 2 bromines? Well, here it matters a lot. So my water is going to come in and I'm going to attack the more substituted side. That's very important because I'm going to have water on one side and bromine on the other side. And if I mix up which side I add my water to, I'll get the question wrong. So it's very important that I'm showing my water adding to the correct side, the more substituted side. And I'm not done. I'm almost done though. All I have to do is finish this out by neutralizing it with a little bit of water. So I'll show that final product over on my page over here. Go ahead and get a good look. Finish up your question or your mechanism. And then our final product is going to look like this. So this kind of makes sense of the fact that I chose to put the hydrin part of the Halohydrin formation on the Markovnikov addition and the halo part of the Halohydrin formation on the anti-Markovnikov. I don't think you can actually classify it as either of those, but if we had to classify it as one or the other, this is what it would be. Okay, so if you have any further questions about this, we can talk about it in recitation this week, or if you're not in my class, you can always post in the comments and I'd be glad to help you out. But hopefully this has helped make sense of some of those additions of halogens to an alkene. Later, haters.